Sorry, it will be not to talk on virtual brains. I just want to say that at first it was supposed that the talk will be on the joint works with Valery Bardakov, and then I saw in the program that he has next talk, so I switched my plans, and I want to speak about another things that I'm actually interested now, and so this will be the title of the talk. I shall explain this. So, starting with the time when I was admitted to the quantum topology laboratory, I started to think, how can I justify such a great honor? And I was trying to think about my experience and possible connections with quantum things. This is actually just some thoughts. This is work in progress, still not yet finished. And even more, there are no applications. So just to answer possible question, what are your construction for? For nothing. So there is no any application. So when I was thinking about this quantum thing, I invited to think together with my recent friends and co-authors. So this construction that I would like to present you is a joint work with Jinyuan Li and Wu Ji. So, as a work, this is maybe the plan of the talk, and as any work on quantum topology, I think it should start with reference to some work of Witten. And here I found somebody from physicists told me about the possible connection, which may be what we know, with some physics. And actually in this work, Witten and Kosa, they are making the variation of the differential. No importance that in his case this is differential is the Durand differential for manifolds. Actually from this I took the idea that maybe it is possible to make a deformation, variation of differential. And actually my talk will be one small construction, how to make variation of differential in some very abstract case. So then these ideas of Witten, they were continued, and actually twisted homology was generalized to the general homology. This is not just to mention. So the basic idea goes very, very far. So we consider the homology of triangulated object, the usual differential which was known by Poincaré. And then also in some recent works there appeared how can we deform the differential in some context of simplicial homology. So this is the basic idea, roughly speaking, what we consider. Let K be just a simplicial complex, and let delta be a function. You can consider any, say, real function or in Z, anything you want in a ring. And then, if you know that there is a usual formula for the differential, if you forget this, so just take the d of v0, v1, vi, vn, and this is equal to minus 1 of a, and then v0, vi, taking away vn. So the idea of deformation is to put function. So in this formula you see that you have simplex here, you have simplex of dimension n minus 1 here, but just consider a function. There will be some condition on this function in order that you get a deformation of differential. And in order to obtain that the differential, the usual formula for the differential, that d squared should be 0. Okay? So yes, this is what I told you. So to deform what we get from this simplicial formula, to deform it by function delta. So what we do, this was the idea of the works of Grigoryan, Muranov, and Yao, and we put everything in simplicial context, and so we generalize this ring in, maybe not generalize, but we consider simplicial group, and we consider the function which we have here, the function, we consider the function as a function of some endomorphisms of the simplicial group, which is given in the data. So, of course, it is not very new, and some similar stuff I found very old paper when this was done in '59. But we are using this in some different context. And in particular, we apply what we construct to the general question of loops on a space. So this is a very classical thing in topology, to study loop spaces for X, and in particular classical works of Marston Morse, I think maybe in 30s of the 20th century, the works when he calculates. So Morse theory was already mentioned today. And not only homology, it is also possible to obtain for the loop spaces on a sphere the cell decomposition. So it gives us the possibility to see that the loop spaces on the sphere is just, you have, say, here the 0 point, and then cell of dimension n to n, 3n, and so on up to infinity. This is definitely very many loops, so this is an infinite dimensional space. And this is a cell decomposition. Another approach to study loop spaces was given by James' theory, who produced a pointed space for if we also start with a pointed space, x and given point, then he produced an object which is actually the free associative topological monoid on X with a given point as a unit. So the free monoid, this is almost the same as free group. I know that in low-dimensional topology people like free groups, so here this is a free monoid. So if you want, you make the following identification. So if you have x and point, say x1, and somewhere you have given point, then again xi plus 1, xn, then because these points should have the role of unit in our free monoid, then this space should be I minus 1 xi plus 1 xn. So you start with all possible sequences, and this is not like a free semigroup, but free monoid. You should make in all possible sequences, you should make the following identification. So this is a word of length n, and this is a word of length n minus 1. So this is evident factorization to get free monoid. So multiplication by this element should be identity. So the remarkable property of this is that you can get a map from this James monoid to the omega of a suspension of x. So you start with the usual map suspension. Sorry, not as sigma I denoted. You start sigma x to sigma x. This is identity. Then this map is conjugate to the map x omega sigma x, and then, so this is a map conjugate to this one, and because this is a free monoid, you can prolongate the map from x to here. You need a little bit I'm teaching, because if you have standard loops, it is associative, and associative only under homotopy, but you can replace by Moore spaces, Moore loops, which are exactly associative, and then you, as in the theory in algebra, you can have a map from free monoid to Moore loops. Moore loops are equivalent to real loops. So this is a map. This is a map of monoids, and remarkable property, I think, James, I didn't put dates, maybe 55 or something like this, that this map is isomorphism in homology. But if we apply now Graham's theorem, then we see that this will be weak equivalence, and for example, for example, if X has homotopy type of CW complex, then we get that this will be real homotopy equivalence. So this is the pathos of the James theory, that for the quite complicated object, almost unknown at the right-hand side, we have this decomposition as three monoids. So this map gives a geometric structure on the space of on the loop space. So this is the remarkable thing. And maybe about the proof, you can use here exactly the three monoid structure. UNet formula to calculate homology. To calculate homology of this, you can use cell spectral sequence, and then this is the idea how James proved this theorem. So now as we want to deform at the level of simplicial structures, we deform by the changing differential in vertices. So we are obliged to work in the simplicial category. So then I here remind some definition. So delta group, I think this is different what delta space that Renat is using, or delta complex, right? So this is very, very formal thing that this is a group, but also it's possible to define delta space. And group means that there are for every n, natural n, there is a sequence of groups, and there are homomorphisms that are called phases, and with evident structure, with evident condition that gives the delta group. Okay, if you add simplicial, if you want to define simplicial set or simplicial group, you should have the degeneracy homomorphisms, which satisfy evident identities. So the usual, the standard example for this is the singular complex for any topological space. So we start with the formal definition for our construction. In particular, we will use the quivers of categories. So formally, we recall that quiver is quadruple. You have the vertices, you have the edges, and the edges are directed, so you have the starting and the target for every vertex, and so the edges are called arrows, and we can write them this way. So we recall that also there is a forgettable function from small categories to quivers. You just consider morphism as an arrow. And now let C be a category, and we recall what is n paths. This is just vertices and morphisms, and also trivial path is defined. So now the standard definition of a nerve of a category, you take the path here, and you in the place I, you just take a composition of morphisms and you obtain di, the phase necessary for the construction of the differential. And the degeneracy operation is that you simply double at each vertex itself with trivial morphism inside. Okay? So now we consider the simultaneously two cases. It may be that K is a simplicial complex or a small category, and VA is the set of vertices, G be a simplicial group, and this is the ring of endomorphisms where we'll get our deformation of the structure. So the definition, the main definition of the talk is that what is a twisted structure on a complex or a category? This is a function delta to the endomorphisms of G satisfying the following commuting rule. It means that if you have 2 points, so what is twisted structure, roughly speaking? You have vertices and you have function at each vertex, say delta V and delta W. At each vertex there is a function to the endomorphisms of simplicial group. We say that this is defining the twisted structure for the category or complex if the following commutative rule is satisfied. So it's not difficult to understand that this condition is given in order to obtain the property of differential, d squared equal to 0. So that the deformation of usual differential will be possible if delta satisfy this condition. Of course, this may be too abstract case, but more concrete, what we call regular twisted structure. This is when we consider automorphism. So delta V takes its values in subgroup. So you have, this is not a group, endomorphisms of G, but you consider now automorphisms, so simplicial automorphisms of G. And if our twisting structure taking place there, we call that this structure is regular. So, okay, so now let K be a simplicial complex, and suppose that it have total order. We can also construct the same way category for it, and you can the same way construct the D and S. And now we start with the main construction. I'm sorry, it's very technical. So what we are doing to construct a delta group in the case of general twisted construction, and simplicial, it will be delta it will be simplicial group in the case of regular twisted construction. So we take a vertex in our set of vertices. It will be the base point, and consider, as usual, the path which is actually trivial, nothing but repetition of the same vertex n times with trivial maps between, it will be the base point for any space of dimension n. And now, the same way as, not exactly the same way, I'm sorry. So maybe having in mind the James construction that I recall that we define this object, which is the main object of our work, as a free product of the same group. So in every dimension, you take a free product, maybe a little bit similar to James' construction. But indices are all not base point element in the paths of A. I remind, A may be the simplicial complex or a category. So you consider it as a quiver, you consider the elements which are paths, and then you take a free product. So formally, it will, you take Gn, and X is a copy of G of X element of S and R. Maybe better to say not it's S and A, but this point deleted. And then we take a quotient group of this product with the relation like this. And sorry for the technicalities. We define the delta structure. So now this delta comes to play. So we define now the differential in our object, and here you see that the same way you have an element, this is a free product, which has the following subscript, this is the index, and then you take away di means that you take away here one vertex and take a composition. But then you are making deformation. Delta is given, so not if delta would be trivial, then it is not the, and in our case actually all essential on our work that in differential we're making the deformation by the twisting structure. So, and this then it is the twisted differential given by this endomorphism, and the sequence of groups forms a delta group. So we prove the proposition that it is a sequence of groups. So now we suppose that this delta structure is regular. So it takes place in the automorphisms, not just in endomorphisms. This gives us the possibility to define the degeneracy operations. Degeneracy operations in such a way that in the place where we were taking the deformation by our twisted structure, we here are deforming by the inverse by some reason in order to obtain, actually it's evident, because you need for the simplicial structure, you need to have the properties like DI/SI is equal to identity. So in some sense, if your twisting structure is not invertible, then you can't get this identity. You should. So it's evident that in order to invert, you are obliged to consider automorphisms of group. So the main thing of this construction is that in the case of regular twisting, we have a real simplicial group. Okay, so this is the main theorem. Of course, I not explain what is this. It also needs a lot of technique to explain what it is. But so the theorem, try to explain. That suppose that now S, our simplicial object, has a regular twisted structure in some simplicial group. So deformation is taken in the automorphism. Then we define a map which this W bar is considered as the classifying space for the corresponding simplicial group. So actually maybe this theorem is not so clear, but the corollary is that it gives us that if you take the geometrical realization, this itself is a simplicial object. But for any simplicial object, you can construct geometrical realization. This will be the CW complex and topological space, if you want. So this is the topological space. And you see that this topological group really has a homotopy type of loops over some space that we also calculated. So in some sense, this is this theorem is in flavor of the James theorem that I wrote down about the GX and the sorry, GX and loops on suspension. Then maybe some example. So let us consider everything as simple as possible. What we take? We take a simplicial group to be the integers, and take S to be a simplicial circle, so simplicial space that actually is a circle. Its realization is homotopy equivalent to a circle. So, and delta B, you consider the automorphism group of Z. This is Z over 2. You take at each vertex non-trivial element. Non-trivial, so our deformation is that in every vertex you take a non-trivial automorphism of our simplicial group. So this will be the deformation. So what do we have? We calculated, it's not difficult to understand, that Cartesian product of the classifying space of this with the circle. So actually the classifying space of Z is also a circle. So you have two circles, and here the delta smash is the same as usual. So you have here the two circles. You have here the Klein bottle, and here is the smash of two. Smash. How it is called? I forgot. Wedge bouquet of two circles. Here this is a Klein bottle. So in Klein bottle you have inclusion of two circles. If you just consider Klein bottle as a quotient of the square, you have inclusion of two intervals, and you see that this object will be nothing but sphere S2 if you put to a point two circles in a Klein bottle. You have just S2, and thus in this case our simplicial group that we constructed is a model for loops over sphere S2. This is the simplest case where our simplicial group works. So this is the case. Okay. So then something about twisted homology that we can have in this case. So in general, when we have not regular structure, it may be quite complicated, and at the moment we are not sure that maybe it is not reasonable. It is not in any case homotopy or some other invariant of the data given here. So so it may be very difficult and very wild in general. We checked in several cases, so maybe not so. Just some illustration about some properties of this, like you know, like Van Kampen. Maybe it's reasonable to say that this is like Van Kampen properties of our construction. So we take this is our simplicial set constructed for a complex, and let it be simplicial sum complex as that the union is K and the intersection is not empty, and let us consider the twisting construction with delta K such that in each K1 and K2 it has a restriction of the general twisted for K. So, and we, as in Van Kampen thing, we took a base point, and for example, we proved the following property of our construction, that the construction for simplicial stuff here is a free product with amalgamation. So everything works because these things are simplicial. So also, if we consider now the case when G is simplicial group, then we have the following exact sequence, so that so it's like a classical Meyer-Vectoris sequence for the homology, that this structure for the intersection, this is direct sum, and this is the abelianization. So everything is abelianization, because this is abelian, this is group, those simplicial, we can take abelianization here, direct sum here, and abelianization here. So I think I stop here.